Hello and welcome to our 32nd session. In today's session we're going to be having a review specifically of the capacitance voltage plots, also known as CV plots, and then we're going to continue our discussion of the MOSCAP structure. MOSCAP, I remind everyone, myself included, metal, oxide, semiconductor, CAP stands for capacitor. We'll be looking at the performance of MOSCAPs, specifically with regard to things like gate oxide and dopings, and we'll be looking at those specifically for the two types of MOSCAPs. The P-type silicon, which is known as NMOS, and it's known as NMOS because the P silicon inverts to N-type silicon at the silicon oxide interface, and PMOS because N-type silicon inverts to P-type silicon at the oxide silicon interface. And finally, we'll be looking, hopefully if we get to it, at some numerical examples. But first, one of my favorite flash mobs, the Brindisi from Traviata, and we'll see you back in about 3.5 minutes.
Liviamo negli lieti callici che la bellezza infiora, e là fuggevo l'ora s'inebria volluta. Liviam dolci fremiti che suscita l'amore, poiché quell'occhio al cuore onnipotente amore fra i gallici più caldiva ci avrà. Amore fra gallici più caldiva ci avrà. Tra voi saprò di vedere il tempo mio giocondo. Tu che follia nel mondo, ciò che a te piace.
Okay, so this is a kind of a broad outline of some of the topics we'll be covering in today's session. We're going to start off with a review of the CV plots. Specifically, we're going to be looking at the CV plots for the NMOS structure, which we hopefully know involves P-type silicon, which is inverted to N-type silicon at the surface. We'll be looking at the 4 different regions: the accumulation region, or negative voltage gate voltages, the depletion region, the weak inversion region, and the strong inversion region. And I should just point out that in kind of a basic course, we really only look at in any kind of detail 3 regions. We kind of skip over the weak inversion region, but I think it's important enough to include it here, and we'll be including it in all of our discussions. And then we're going to look at the MOS, the metal oxide semiconductor structure, give some examples both for NMOS and PMOS, then some numerical examples, a table which summarizes basically the whole thing, and we'll then go on to 2 work problems which illustrate some of these concepts from Chapter 19. Chapter 19 is the chapter which is work problems in metal oxide semiconductor structure, and we'll end with a joyous rendition of part of the overture to Strauss's wonderful operetta, Die Fledermaus, the Mouse. Okay, so let's start off with a review of the CV plot for NMOS, and here it sits. This is from Chapter 31. There are 4 regions labeled 1, 2, 3, and 4. Accumulation, depletion, weak inversion, and strong inversion. And this almost looks completely symmetric, but not quite. And that's a good thing, because if it was completely symmetric, in other words, if this thing was like a bowl here, and it was completely rounded, and you couldn't tell the left side from the right side, we really wouldn't have a way of knowing that this was NMOS. But fortunately, that's not the case, and the fact that it has this inverse relationship to the depletion region here, and it's not symmetric, gives it away. So, and we'll see that in just a minute. So the flat band is the demarcation between accumulation and depletion. V1 is the point where the Fermi level crosses the intrinsic, or I should say the intrinsic bends down so that it touches the Fermi level. VT is the threshold. Sometimes I'll write it as VTH, but it's the same thing, VT or VTH. That's the threshold voltage. And of course we have the strong inversion. These levels here are both Cox. Almost doesn't look like there's these should be exactly the same level here. Okay, so that's basically what I'm saying here, that we have the 4 different regions, and there is a lack of symmetry, and that lack of symmetry is really important. Okay, and the lack of symmetry is caused by the shape of the structure in the depletion region. In this region, C, and I should mention here that C is the areal capacitance. It is farads per square centimeter. Actually, it's not farads, it's probably picofarads. They're very, very small values, or nanofarads. And the thing is here that C is inversely proportional to the depletion width, and we'll see that in the pictures in just a little bit. And the depletion width is proportional to the square root of the gate voltage VG. And if we do have a Pmos structure, we'll be able to know that right away, because the Pmos structure would be the mirror image. If I shined a mirror on this thing right here, everything would be flipped. It would go down very slightly here, and then all of a sudden, boom, it would go up rather abruptly. So it would be the mirror image of the NMOS structure. And here we see those 4 regions pictorially. In accumulation, we have essentially, not essentially, but generally a negative voltage on the metal, on the gate, and we have positive mobile holes which are attracted to the interface between the oxide, which is here, and the silicon. So this looks just like a parallel plate capacitor. Let me just jump over to strong inversion. And in strong inversion, it's basically the same thing. We have, in this case, positive charge on the metal and negative electrons, these are minority carriers, on the interface between the oxide and the silicon. So the important thing about the strong inversion is that the capacitance is dominated by the larger of the capacitances, which is the oxide capacitance. So remember that capacitors in series, there are two capacitors here. There's the oxide capacitance, just like here, charge on the two electrodes, and then there's the depletion capacitance. But the depletion capacitance is relatively small compared to the oxide capacitance. So the oxide capacitance predominates, and that's why the areal capacitance in accumulation and strong inversion are essentially equal, and they're equal to Cox. In depletion, which is region number 2, we have no mobile electrons at the interface. Everything is depletion capacitance, and we increase, in a positive sense, the voltage on the gate. And what happens to this region? It grows. It gets bigger and bigger and bigger, and therefore the capacitance gets smaller and smaller and smaller, because the capacitance is always inversely proportional to the width. In weak inversion, we start to push a couple of mobile electrons onto the interface here, and every time we increase the positive voltage on the gate, we attract electrons to the interface, and therefore this width basically stays the same, and that's why the capacitance basically stays the same until we get to strong inversion and or threshold, which is the demarcation between weak inversion and strong inversion. All of the area in the depletion region now is shielded by these negative mobile electrons. No fields can get through, so all future charge, as I increase the positive voltage on the gate, charge is only attracted to the interface, and the capacitance remains constant at Cox. So now to calculate these capacitance, it's fairly straightforward in the three regions. In region 1, the capacitance, the areal capacitance, is Cox, which is the permittivity of the oxide divided by the oxide thickness. In depletion, the capacitance is approximately equal to the permittivity of the silicon, not of the oxide, which is about 3 times larger than the oxide, divided by the depletion width. The depletion width itself is a function of, this is not W times Vg, this is W as a function of Vg. So if Vg grows, W grows, and C goes down. And that's exactly what we're showing here. As W grows, C goes down. In weak inversion, we reach a W max, the depletion region kind of maxes out, and therefore the C is approximately constant, and then in strong inversion above threshold, it jumps up again and is equal to the oxide capacitance, just as we have in accumulation, although the charge senses are opposite. Here it's negative, positive, here it's positive, negative. So that's pretty much what we have. One more little detail, actually it's not little, it's a detail, but it's actually kind of important, which is, it's also quite interesting. Both in the weak and strong inversion regions, where do the electrons come from? The electrons come from the P silicon. In both of these regions, we have electrons, which only, I'm not saying electrons, I'm talking about mobile charge. Electrons at the interface only come from the P silicon. Here we don't have to worry about it in depletion, because here these are uncovered negative fixed ions. These are acceptor ions like arsenic, which have accepted an electron and become negative fixed ions in the lattice. But in weak inversion and in strong inversion, we have electrons at the interface. These are minority carriers in the P silicon. And, well, they come from the P silicon, but there's not too many of them. And they have to cross over this rather large depletion region. This can be a fairly large fraction of a micron. It might be 0.3, 0.4, 0.5 microns. So all of these electrons, this is the source out here, and they have to travel through the depletion region, and it takes time. Well, if we sweep, don't forget what we're doing. This is a very practical device. It's a very practical plot. There are actually machines that you can go out and buy which give you CV plots. And what it happens, I probably should have mentioned this, I think I did the last time. What we do is we sweep the voltage, the gate voltage, from accumulation to strong inversion. And there's a rate of sweep. We can sweep it slowly or we can sweep it quickly. If we sweep it slowly, there's lots of time for these electrons to kind of work their way from the P silicon into past the depletion region to the interface. But if we sweep it very quickly, they don't have time to do that, and there's no time for these little guys to show up. And what happens in that case is, well, the depletion region keeps growing, and that's called, I believe, what is it called? Something, deep depletion. I knew it was called something. So that's what we're showing here. In a slow sweep, we get this nice CV plot, but in a fast sweep, we have a situation where the depletion or the capacitance, the area capacitance, keeps going down, and that's what's shown here. So if we sweep fast, we can get an idea of some other parameters. We're not going to go into that in detail, but so whenever you see something that looks like this in a CV plot, you'll know that these are minority carriers, and there is a fast sweep, and they haven't had time to accumulate at the interface. Okay, before we go on to the new material, I'd just like to go over an example which we went over, which we introduced in the last session, and basically what we're looking at here is the range from V1 to VT, and we're going to look at that for two different gate oxide thicknesses. So let's start with the example that we were looking at in session 31. We have an NMOS capacitor, so it's the same shape that we have here, doped to 10 to the 17th, that's a moderate doping, and we have an N plus poly gate. So we have a flat band voltage of about a volt or so, and we have about 34.5 angstroms gate oxide thickness. Why did we use this? We'll see in just a second. Actually, right here, we use this particular value of gate oxide thickness because it gives a very nice C-ox of 10 to the minus 6 per square centimeter. Again, an aerial capacitance. The flat band voltage was about minus volt, and we saw the threshold voltage. We just put all that stuff in. Pretty straightforward flat band voltage. We use 2 phi-B, where phi-B is the bulk potential In the P silicon, if it's 10 to the 17th, that's 0.42. 0.42 times 2 is 0.84. And the reason that we have the 25B is that the silicon surface is just as N-type as the bulk silicon is P-type. So it's N-type plus P-type, and the P-type is 0.42, so it's twice 0.42. And that's why we have 0.84 and 0.84. The Cox is a very nice value, 10 to the minus 6. The doping is 10 to the 17th. The silicon permittivity is about 10 to the minus 12. This is rounded off, but as I say, close enough for government work. And we have the 2Q. So we find a very low value of threshold. And that's probably a good thing. That's not, we don't have to work very hard in our gate voltage. Only a gate voltage of plus 0.02 volts sends this thing into strong inversion. In this case, the flat band voltage is minus 1 volt. So it's over here. This is about 1 volt here. And the VT is shifted all the way over, so it's essentially at the origin. Okay, the flat band voltage was 0. This whole thing would be shifted to the right, so the flat band voltage would be at the origin. So then we ask the question, and I'll ask it again: what is this point V1? Point where the intrinsic line, the intrinsic concentration, crosses the Fermi level. That's when we have an interface or a demarcation between depletion and weak inversion. So instead of having 2 phi b here, we have 1 phi b. And if we put all those numbers in, we find that that value is minus 0.44 volts for the gate voltage. And again, that is not represented here. This guy V1, which is that value that we just calculated, is way over here, so it shifts over. This is minus 1 volt, and this V1 would be about almost minus a half a volt. So this line here is shifted rather dramatically, the vertical axis. Okay. So what it means is for gate voltage less than or more negative than minus 0.4 volts, there should be a minus sign here, we're in depletion. For VG greater than minus 0.4 volts, but less than 0.02 volts, we are in weak inversion. So minus 0.44 plus 0.02, this region of about close to a half a volt, 0.46 volts, is the region of weak inversion. That is not a good region to be in. We'd like to make that as small as possible. And the reason that we'd like to make that as small as possible, because in weak inversion we have some mobile electrons, and those mobile electrons at the interface, at the silicon oxide interface, the silicon surface, can conduct electrons, and that is how the FET, the field effect transistor, works. So we can have a finite current if we put a voltage on that across that region. So we'd like to make that region as small in voltage as possible. And one can argue here that really intrinsic is a little bit extreme, because at intrinsic we really don't have any mobile electrons at all. In fact, we don't start really accumulating any measurable amount of mobile electrons until we're well into weak inversion. So instead of having the gate voltage at VB, where the intrinsic crosses the Fermi level, let's make it 1.3 or 1.5 even times the bulk potential. So then we'd be going from minus, approximately, you can work this out, you would get a new gate voltage corresponding to V1, and it would be, instead of minus 0.4, it would be more positive than minus 0.44, and let's say about 0.3. So that is really a little bit more realistic, but even about a third of a volt, it's very possible the gate voltage would be in that region, and we would have a finite current where we don't want it, and that is not a good thing. Okay, so another detail, just to prove that the Cox is actually 10 to the minus 6, you put in all those numbers for 34. This actually probably should be 34.5, but I'm a little bit sloppy here. The oxide permittivity is the silicon permittivity divided by 4. So that's why we have 4 divided by 12. And that's how we get the 10 to the minus 6 farads per square centimeter for the areal capacitance in either either in accumulation or in strong inversion. Now, the reason that we go through this little exercise is, suppose I increase the oxide thickness. Was 34.5, I multiplied by 10. Unrealistic? You bet. But the whole idea is to show that we like to make the oxide thickness as small as possible. So in that case, if we have a greater oxide thickness, as Tox goes up, Cox goes down, and in fact, exactly as we'd expect, there is a factor of 10 decrease in the C oxide as the T oxide increases by a factor of 10. And then we get a new threshold voltage, not minus and not 0.02 volts, but plus 1.5 volts. And that makes complete sense, because the larger the oxide thickness, the further away the gate is from the, let's go back here, further away the gate is from the silicon, and the less control the gate has on what happens to the silicon, and the more voltage we have to place on the gate, either in weak inversion or in strong inversion, in order to invert the silicon surface. So that all makes sense, that we have a much higher threshold voltage for a much larger gate oxide thickness. And that is quite an increase. It was plus 0.02 volts, and now it's plus 1.5 volts. And we can go through the same exercise that we went through before, looking at where the onset of reconversion occurs. That's this value of V1 right here. That's where we have the interface between depletion and reconversion, where the intrinsic crosses the Fermi level. And let's do that again. Same deal. Flat band voltage, but here instead of 2 phoebe, 2 times the bulk voltage, we have 1 times the bulk voltage, so it's 0.42 here, and we calculate all that out, and we get a value of about 0.6 volts. So what's happened here is, and I'll just read this off, not only did the threshold voltage and the onset of weak inversion increase. Well, remember that the threshold voltage is 0.02, now it's 1.5, but the difference between the onset of weak inversion to the onset of strong inversion increased from about 0.46 6 volts, this region here, to almost 1 volt. That is big. So from less than 0.5 volts, it increases to nearly 1 volt. That is not good. That is not good at all. We want to make it smaller. So what we've done here is do exactly the wrong thing. We increased the gate oxide thickness, and I said, well, boy, we really need to make this smaller. And that is a good thing. We want to make it, in fact, smaller, in fact, much smaller than even 34.5 angstroms. And now we're well below 20 angstroms. The smaller it is, the more control the gate has over the silicon, and the narrower or the smaller this region is between weak inversion and strong inversion. Okay, so in this section we're going to attack the NMOS structure again for the umpteenth time, perhaps. Hopefully it won't be too boring, but we're going to do it from the standpoint of the energy band diagram. So let's go back and consider the same basic structure. It's a P-type silicon, which means it's an NMOS structure. The doping is the same, 10 to the 17th, and we're going to initially start at equilibrium with no gate voltage, and we're going to start with the flat band voltage equal to 0. So flat band voltage equal to 0, all of the bands are straight, and then what we're going to do is we're going to decrease or make the gate voltage a little bit more negative, and the P bands are going to band up, and you might recall that that is in accumulation. And what happens here is, because this is negative on the gate metal, then the gate metal rises in value, and we have a situation where we have a slope, a negative slope on the oxide and a negative slope on the bands in the silicon. The band bending in the silicon is about 3 times the band bending in the oxide, because the permittivity is 3 times as high in the silicon as it is in the oxide. So this structure is in accumulation, not a very interesting structure. So now we're going to flip the bias on the metal, and we're going to put a positive bias on the metal. And then we get the P bands bending down, and the oxides also having a positive slope. Notice again that the slope on the oxide is the same as the slope on the silicon, except the value of the slope is somewhat less in the oxide. And here we're pushing the metal down with a positive voltage. And we see from the diagram that this particular energy band diagram shows a structure in depletion. And you say, well, this looks pretty similar, except the bands bend up here and the bands bend down here. How do I know this is accumulation? And how do I know this is depletion? Because here, the surface right at the oxide silicon interface is more P than in the bulk. Why? Because the Fermi level is actually closer to the valence band. Here it's about, this distance here is 0.42 eV, and so whatever this distance from here to here is about 0.56. So whatever that difference is, I don't know, 0.18 or something, it's closer here. So it's more P here than it is here, and therefore we have positive charge at the interface, and there is no depletion region at all. Whereas here, the surface is less P, and the only way to make the surface less P is to uncover negative, and that's because it's P silicon, there are negative fixed ions at the surface. So here we have negative fixed ions right at the oxide silicon interface, and we have a situation of depletion. Now I just want to make a little bit of a detour here. Suppose this was in equilibrium. Suppose this was with no gate voltage, and I wanted to know what the sense or the sign of the flat band voltage. Well, here it's negative, here it's positive, so the internal electric field in that particular case would be in the positive direction, plus to minus. In order to unbend these bands, I have to put a external field which is in opposition to the internal field. That's what forward bias is all about. So I put a field which is plus over here and minus over here, which is to say in the negative direction. Plus, minus points from right to left. Therefore, the flat band voltage would be negative. And that is always the case for a situation in which in equilibrium we have a depletion in the silicon. That means that the metal work function is less than the silicon work function. Flat band voltage will always be negative, and we saw if we had, it, for example, an N plus degenerately doped metal for the gate and a P silicon of 10 to the 17th doping, the flat band voltage is about minus, emphasize the word, minus 1 volt. Okay, let's trudge on. And there's just a little note here that really we have a connection between the back end of the silicon and the metal, and charge always flows from the back end to the metal or vice versa. But this is where the action takes place, because this is where the charge accumulates. So if I have positive charge at the metal oxide interface, I'm going to pull over negative charge from the oxide silicon interface. So this is where all the charge occurs. There's no fixed charge or even mobile charge here. This is all quasi-neutral, and here, of course, since it's a metal, it is certainly neutral. So now we look at the situation of the structure where the metal work function and the silicon work function are not equal. And the first thing we have to realize is when we have difference in work functions between the metal and the silicon, the flat band voltage is not equal to 0, and we're going to either in equilibrium be in accumulation or in depletion. So let's start with the non-ideal case for P silicon, where the metal work function is greater than the silicon work function. And in that case, we're going to be in accumulation at equilibrium. The P-type silicon surface becomes more P-type than the bulk, and we have positive charge here at the oxide silicon surface and negative charge on the metal surface at equilibrium. This is not an equilibrium if the work function difference is such that the metal work function is greater than the silicon work function. In P silicon, we have accumulation at equilibrium, and if we apply a negative bias to the gate, the band bending will increase up in the P side at the surface, and we go even further into accumulation. So in order to go into depletion, we have to make the gate voltage much more positive than we would if the metal work function were more quote-unquote normal. And that's the second case we're looking at, where the metal work function is less than the silicon work function in p-type. And in that case, we start out at equilibrium with no gate bias in depletion. And if we apply a negative gate bias, then we can go to flat band, and then eventually, if we continue to increase the gate voltage in the negative direction, make it more and more negative, we can go into accumulation. So the flat band voltage will always be negative, and here it's just equal to the magnitude of the difference between the work functions and as I said before, but just worthwhile repeating, the way to think about this is to think about the metal as or the metal and silicon being a p-n junction. And if we have a p-n junction which always is rectifying, the p silicon will be on the left in this particular case. That's here because it's a p silicon. The n silicon will be on the right. And for p-n junction with the n, I should say the n is on the left and the p is on the right. Sorry about that. So the n will always have a Fermi level which is higher than the p. So the work function on the metal / n-type will be less than the work function in the silicon. So if we apply a positive voltage to the gate structure, it will become more depleted, eventually moving from depletion as we increase the gate voltage in a positive sense to inversion as the gate again becomes more and more positive. For n-type silicon, same concepts, but everything is flipped on its head. And we summarize that in a table. So first we have the metal work functions are equal. So this is be considered flat band at equilibrium. There's no band bending on either structure for NMOS or for PMOS. And we have a comparison with the metal silicon structure, the Schottky. Here we'd have an ohmic contact. So for all these cases, we would have an ohmic contact. For gate voltage less than 0, we have accumulation. Gate voltage greater than 0, we have depletion. And notice that the PMOS with n-type silicon is exactly reversed. So whatever we have here, we have the opposite for PMOS. And now we have the quote-unquote normal case where the metal work function, at least for PMOS, or I should say for n-type, for p-type silicon, if we have the metal work function less than the silicon work function at equilibrium, we have depletion. And if we have the metal work function greater than the silicon work function at equilibrium, we have accumulation. And we can have, in those particular cases, rectifying junctions for the Schottky. Now we're going to look at some numerical examples, and we're going to start with the flat band voltage equal to 0. The work function difference is 0, and we're going to start with a large oxide thickness and moderate doping. Moderate doping would be 10 to the 16th. Notice it's acceptor doping, which is consistent with p silicon. More normal doping today would be about 10 to the 17th, but this is the real issue here. We're starting with 1,000 angstroms of gate oxide. that is really thick. So what's the first thing we think about with this large gate oxide? We're going to have less control. The gate, I should say, is going to have less control over what happens to the silicon surface than if we had a smaller gate oxide. So this gives us a relatively, not relative, really extremely small or large C-ox. Well, as the gate oxide becomes thicker, the oxide capacitance becomes smaller, and that's not so good. Okay, so I'm going to ask what kind of structure we have for the following conditions at equilibrium, at a gate voltage of -1 volt, +1 volt, and at +2 volts. And then finally, we're going to find threshold voltage. Okay, so given the fact that the substrate is P-type, we expect the threshold voltage for a work function difference 0 to be positive, generally positive, and we're going to find that. First, let's find the gate oxide, or the gate oxide capacitance, C-ox, excuse me, which is just equal to the permittivity divided by the oxide thickness. Again, this is the areal capacitance, so the units are farads per square centimeter, and the gate permittivity, or I should say the oxide permittivity, is here, and the oxide thickness 10 to the -5th, so we get a relatively small value for the gate oxide capacitance. Okay, so of course, first case where we have equilibrium, flat band, there is no charge any place, and there are no uncovered fixed ions, and of course there is no depletion region. At -1 volt, then I have a situation where, let's see, this is the case we just looked at in our energy band diagrams. This would be in accumulation. Now, it doesn't matter what the oxide thickness. Put -1 volt for work function difference equal to 0, I'm in accumulation. I may not be as great in accumulation, or maybe less, depending on the work function difference, but certainly it's going to be accumulation. Okay, and that's now +1 voltage. Well, if I was in accumulation with -1 voltage, I can pretty well guess that I'm going to be at depletion with a positive voltage of +1 volt. And since I'm in depletion, I'm probably going to have some band bending. Well, this is the basic formula for band bending, which we've seen quite a number of times, and I put in all the numbers here. The Q is here, the NA is here, this is now not the oxide permittivity, this is the silicon permittivity, 10 to the -12th. And notice the oxide permittivity is less than the silicon permittivity, and the 2 times the gate oxide capacitance. Put in all this good stuff, and I get a silicon bending of about a quarter of a volt, and it bends down from neutral to surface. It bends down. Now I'm putting in +1 volt. Well, where's the other? I've only got 0.23 volts dropped across the silicon. It must be that the remainder of that 1 volt is dropped across the oxide, and of course that makes sense. Now, why is more voltage dropped across the oxide than across the silicon? And the reason is the oxide thickness, T-ox, is very large. And that's what we expect. If we had a smaller oxide thickness, we would expect these numbers to be reversed. We would expect more voltage to be dropped across the silicon and less to be dropped across the oxide. And of course that is consistent with the fact that the smaller the oxide thickness, the more control the gate has over the oxide surface. Okay, that's a mouthful. And finally, if we put a gate bias of plus 2 volts, we would expect both of these numbers to go up. It may be in depletion, it may be in weak inversion, or maybe inversion, but one thing's for darn sure, it ain't in accumulation. So we're moving now from a depleted region, possibly either into weak inversion or strong inversion. And if you put in the numbers, and I urge you to do that, we get the following values. Again, these values must add up to 2 volts. We drop a little bit, or we drop some of it across the oxide, and we drop, this is the voltage dropped across the oxide, and we drop 0.68 volts across the silicon. Probably easier to do the silicon first. Just put in all the numbers and we get 0.68. More than double, by the way, the value at 1 volt. So the silicon bending increases quite a bit more than we would expect. It's not linear by any means. We increase the voltage by 1 volt, and it increases by well over twice the bending that we had for the smaller value. And that places the structure very close to threshold, and we can prove that by calculating the threshold voltage. And that's what we do here. This is the demarcation between weak inversion and strong inversion. That's why we have 2 times the bulk. And of course, so what is the bulk voltage? Well, we recall that we somewhere back up here we had 10 to the 16th. So if we have 10 to the 16th, the bulk V sub B, which is someplace, oh here it is, V sub B would be 0.36. Now we have been working with a doping of 10 to the 17th. 10 to the 17th of VB would be 0.42. But remember the rule of 60 millivolts. If we decrease the doping by a factor of 10, the VB goes down by 60 millivolts. 0.42 minus 60 millivolts brings us to 0.36. 2 times 0.36 is 0.72. So that's where the 0.72 comes from here. And same thing here. And we get a threshold voltage of 2.08 volts. So indeed, way back up here, we were very close to threshold. And if we're dropping 0.68 volts across the silicon at plus 2 volts, at threshold, we're dropping maybe 0.7 volts, and all the rest of the voltage as we make the gate more positive will be dropped across the oxide, and the drop across the silicon is going to be constant, or we say pinned at about 0.7 volts or so. Okay, now let's look at the effect of work function on all of this. So if the work function is not zero, the first case we considered the work function was 0, work function difference. So now we're going to consider work function difference not equal to 0. And we start with the non-ideal case or non-preferred case where the metal work function is greater than the silicon. Of course, in that case, as we've said a number of times, if we have equilibrium, we will be in accumulation. At minus 1 volts, we'll be even more in accumulation. At plus 1 volts, well, that's going to take us close to flat band. Remember that we had this particular condition. Yeah, here it is right up here. The flat band voltage is positive. So if we had, for example, a 1 volt difference between metal and silicon, then the flat band voltage would be about 1 volt. at the gate voltage of 2 volts, we would, well, we don't know. We'd probably still be in depletion. We're not sure. We have to work out the numbers, and it works out. And without doing it, you can show very easily just by putting into the threshold voltage calculation here. The threshold voltage is now 3.08. Well, that's interesting. Here it was 2.08. Now, if we had a work function difference here of 1 volt, that gives us that difference in 1 volt here. And again, that is consistent with the fact that the flat band voltage is simply a shift, a translation, either left or right. And finally, if we look at the situation, which is the more normal situation, where we have metal work function less than silicon work function, think, for example, an N++ degenerately doped gate metal for phi sub m, Fermi level higher on P silicon, and then we have a flat band voltage of about -1 volt. For Vg equals 0, we will have depletion. For Vg equals 2 volts, we're probably going to have strong inversion because the threshold voltage is quite reasonably low. Okay, so again, 1.1 volt or so positive for threshold is not too high, not too low. It's kind of in the middle. We're going to examine threshold voltage of just over a volt or so is not too high, not too low. It's kind of in the middle. And the important thing is that the work function difference, flat band voltage, shifts the threshold up or down. And when the structure is in depletion, the relative distribution of the voltage drops across the oxide and the silicon is not, I probably should put that in bold, is not affected by the flat band voltage. It is only affected by the gate oxide thickness and the doping of the silicon. Okay, let's go on to the effect of doping. So the first example, everything we've done in this previous part of the section had a doping density of 10 to the 16th for the P silicon, except, of course, because it's P. Okay, now we can reason that if the doping were to decrease, and we're going to do that in just a little bit, to 10 to the 15th, our reasoning is that the threshold voltage will decrease in magnitude. All of the parameters being equal, that's important, because at a lower doping, the intrinsic is closer to the Fermi level. The Fermi level is higher up, and the closer the Fermi level comes to intrinsic, the easier it is to push it over to the other side. So it makes sense that with a lower doping density, we should get a smaller threshold voltage. Okay, and we're going to see, of course, at 10 to the 15th, the Fermi level is 0.3 eV below intrinsic versus 0.36 for 10 to the 16th, and as we've seen, 0.42 for 10 to the 17th. Each decade is 60 millivolts. But before we go there, this is logical, it's intuitive, but this logic seems to contradict the results that we have already obtained. In our first case, going back quite a number of pages, maybe 6 or 7 pages, we had 10 to the 17th, we had the flat band voltage of about -1 volt, and we had a threshold voltage which was extremely low, plus 0.02 volts. While the case we just considered here, we had a threshold, same conditions, except for the lower doping, we had a threshold voltage which is higher, exactly the wrong way. So what's the resolution? Well, there's a very simple resolution. In the first case, with the higher doping, 10 to the 17th, and the smaller VT, 0.02, the oxide thickness was extremely small, 35 angstroms, versus the case right here where the oxide thickness was 1,000 angstroms. So the issue here is the weight of the oxide thickness, the influence of the oxide thickness far, far outweighs the influence of doping. So we're going to repeat that calculation now for a lower doping and then for a higher doping, but we'll save that for the next session. So, wow, we're going to have to really jump down. I'm afraid we're going to jump down about almost 10 pages. Yikes! Well, we'll do it again, as long as we're having fun. And talk about fun, I think this is really going to be fun. Let's listen to a video clip from the overture to Johann Strauss's Die Fledermaus, and we'll see you next time.